So ultraviolet light absorption. Every molecule can absorb ultraviolet light. And what's going to happen is when a molecule absorbs ultraviolet light, it can promote an electron from a lower energy state to a higher energy state. Ultraviolet light has a slightly shorter wavelength and thus higher frequency than visible light, and it occurs mainly in the 200 to 400 nanometer range. Remember, we see colors in the 400 to 750 nanometer range. When electrons in a lower energy state, known as the ground state, absorb light having the appropriate energy, an electron is promoted to a higher energy state, known as the excited state. The energy difference between the two states depends on the location of the electron. And you might remember this from Chem 111 where we talked about h nu, E equals h nu, and the Bohr model of the electron. Well, what we're going to see is the energy difference between these two states depends on the location of the electron. So if I know E equals h nu, or E equals c over lambda, I can then know how much energy is needed to promote that electron to the excited state. With conjugated dienes, electrons in the sigma bonds and unconjugated pi bonds requires light having a wavelength of less than 200 nanometers. Therefore, we're going to only see ultraviolet radiation absorb in conjugated systems. The conjugated dienes are going to have a slightly longer wavelength than we would see with an isolated, unconjugated pi system. The wavelength of the UV light absorbed by a compound is often referred to as its lambda max. For example, 1,3-butadiene has a lambda max of 217 nanometers, whereas 1,3-cyclohexadiene has a lambda max of 256 nanometers. As you increase conjugation, you increase the lambda max. 1,3-butadiene has a lambda max of 217 nanometers. 1,3,5-hexatriene has a lambda max of 268 nanometers. And when we finally go up to having 7 double bonds, if I can actually count today, oh, actually 6, sorry, it has a lambda max of 364 nanometers. Compounds take on the color of the light it does not absorb in these cases. Let's take a look at lycopene. Lycopene absorbs visible light at 470 nanometers, which is in the blue-green region of the visible spectra. Because it does not absorb light in the red region, lycopene appears to be bright red. Why is this important? Later on in the semester, we're going to perform an experiment where we're going to synthesize a sunscreen. Ultraviolet radiation from the sun is high enough in energy to cleave bonds, forming radicals that can prematurely age skin and cause cancer, melanoma. However, since much of this radiation is filtered out by the ozone layer, only ultraviolet light having wavelengths greater than 290 nanometers reaches the Earth's surface. Much of this ultraviolet light is absorbed by melanin, the highly conjugated color pigment in the skin that serves as the body's natural protection against the harmful effects of ultraviolet radiation. Prolonged exposure to the sun can allow more ultraviolet radiation to reach your skin than melatonin can absorb. Therefore, people use commercial sunscreens to offer better protection against ultraviolet radiation because they contain conjugated compounds that absorb ultraviolet light, thus shielding the skin for a limited time from exposure to harmful ultraviolet radiation. Commercial sunscreens are given an SPF rating, sun protection factor, according to the amount of sunscreen present. The higher the number, the greater the protection. Two sunscreens that have been used for this purpose are para-aminobenzoic acid, PABA, and Patamate O. We are going to make a different sunscreen in lab at the end of the semester.